Hello and welcome to Intro to Backend Development, Lecture 3 on Relational Databases. Let's just review what we covered in the last lecture talking about databases for single tables. So imagine we have a client and a server. Clients initiate a process by sending a request to a specific server. The server intercepts this request, triggering a route within the code, which then leads to data operation, whether it's retrieval or creation of new data, and then it will return a response back to the client. What's changed now from last lecture is how we're messing around with the data operation, and we're introducing the notion of a database. So servers communicate with databases via SQL commands, and then the database will retrieve the data or update the data or whatnot and return that back to the server via SQL. For us, we'll be using the SQLite 3 Relational Database Management Service along with its Python packages to execute these SQL commands in our Python code. After the server has received this data from the database, it can then return a response back to the client. In total, looking at the whole process, a client will initiate a request, the server will initiate a SQL command to fetch data from the database, which will be return some data, and then finally the server can return a response back to the client. We also covered the notion of a single table database in last lecture. So tables structure information into rows and columns where columns represent a specific field with an associated data type. So for example, we would have an ID field that's of type integer. We may have a string field called name to represent the name of a person if this table is representing individuals. And then rows represent a collection of each column in like one instance. So a row in a database for a user would represent one person. So you would have many rows to represent X many people. And then we query and manipulate data with SQL, a new language, the structured query language that we've been introducing you to and that we want you to learn how to use effectively with the upcoming assignment as well. So now we're going to move on to relational databases. So high overview of what relational databases are. They just allow us to establish and structure relationships between data. So answer questions like this, like what comments belong to which posts, which users are friends, which transactions relate to which senders and receivers, and then in the case of like this upcoming assignment with Venmo. So understanding how that our tables may be separated, but there's a relationship inherently between in an application between different tables. So we use a relational database to structure information in that form. So consider we have two tables here, one that's a user and one that's a post, say for like a social media application. You can see that a post table has this column called author, and in author we can store the IDs of users in the user table. So as you can see here, author 2 corresponds to user with ID 2 in the user table, which is Jane. We call these specific columns that represent IDs on another table foreign keys. So a foreign key is a column in one table that uniquely identifies a specific row in another table. It can be the same table or also a different one. And we can also call these secondary keys. So in our example before, an author field in the post table referred to a user ID belonging to a user row. So in any case where we have a foreign key column in our table, it implies that we have a relationship with another piece of data belonging to another or the same table. So there are three main archetypes of relationships: one-to-one, one-to-many, and many-to-many. First, starting with one-to-one, we define this as kind of like a single row in a table A can refer to only one row in table B, and vice versa. Table B can only refer to one row in table A. So this diagram you see in the top right, you can imagine the two columns as separate tables, and then the lines connecting them represent that relationship. So each row can only be related to one other row. So an example of this would be students and net IDs. So you as a student, you can only have one net ID. It's assigned to your person. And similarly, a net ID belongs to only one student. I'm the only person with my net ID. No one else has it. And my net ID only belongs to me. So one example of how we would want to implement like a one-to-one relationship in an application would be a discrepancy between users and profiles. So in the case of our user table, we would have like an ID of 10, and as we can see in the profile table with user ID column, the foreign key column, we also have one reference of user 10. And then the same thing for user ID 20 corresponding to Jane in the user table. We may want to create a separation in an application between users and profiles if we want users to, if we want like profiles to be something we expand upon or relate to other aspects of our application, or even external applications that may not want to be tied directly to a user, which may have more like sensitive data relating to them. So here's an example of SQL we would write for this implementation example. So a user would just have an ID in the name column with integer primary keys, text not null, and then a profile. What's unique about this table is that the last two lines, the user ID column definition. So we say, hey, it's going to be an integer with the same type of the ID field in the user table, and we're also going to use this flag unique. Unique enforces that it's like a unique item within the entire column. So if I have one row with user ID equals 20, and I try to add a new row with user ID also equal to 20, SQL will automatically throw an error for us to let us know that we're breaking the unique constraint we set on this column. So then after we define a column to represent our foreign key, we have to explicitly tell SQL that this is a foreign key. So we use this with foreign key syntax highlighted below. So foreign key user ID references, and then the table name, and then in parentheses the column within that table. So for us it's the user table and the ID column. This is an example of how we would insert into both of these tables respectively. So we'd say inserting into the user table, I just have to provide the name John, or if I'm inserting into the profile table, say I'm setting a status in the user ID, I can just simply add in the ID in string as I would normally with any other columns. The next relationship type we have is one-to-many. So as you can see from the diagram, so one item in one of our tables can be related to many rows in another table, but each row in the second table can only be related to one row in the first table. So an example of this would be posts and comments that we worked with from the first assignment. So each post can have many comments, but each individual comment can only belong to one post. Like when I comment on my friend's Instagram post, that comment belongs strictly to that post and it's not referenced to anything else. And at the same time, like a post can have a massive thread of all these comments on it. So one example we'd consider is maybe if we're making like a Spotify or Apple Music retake, an album in a song table. So as you can see with ID 10 on the album table, we can have multiple songs listed that correspond to that same album. So you can see here for Igor, we have Earthquake and I Think, while for 444, we could have more songs associated with that, with those respective IDs. So here's an example of how we would implement this with SQL commands. So creating table album is similar to before, just ID name, primary keys, not null. But what's unique about this approach is creating a table for songs. As you can see highlighted in green, the album ID column definition, we took away that unique constraint we put on the one-to-one relationship. We just simply now say not null. So every song that's created has to be related to a specific album, but we're not enforcing that those album IDs have to be unique. In fact, like that's the whole purpose of one-to-many is I have many songs that can reference the same album. And then just as before with the one-to-one relationship, when we're establishing this foreign key, we have to explicitly say it after the column definition. Foreign key album ID references the table album and the ID column within that table. So here's an example of how we would insert into the song table and then query from it. So inserting is just normal as before, but we can use the query to say like I wanted to get all of the songs belonging to a particular album. I would just say select star from song where the album ID column is equal to a particular ID. So the third and final relationship we have to talk about is many-to-many. As you can tell from the diagram, so we can have one row in a particular table can reference many rows in a second table, and then vice versa. One row in the second table can reference many rows in the first table. So one example you may want to consider like posts and hashtags. So each post can have many hashtags, and similarly if you search for a hashtag you can see all of the many posts that are associated with it. So the implementation of a many-to-many relationship is actually more complex than the prior two, and we have three maybe potential choices that we would consider when actually implementing this in our own application. The first two of which are not ideal, and I'll go through why. So the first, what if we wanted to have multiple columns to store more foreign keys? So say we're considering like a CMS setup where a student can be enrolled in many courses, and a course can contain many students. Maybe for a student table I consider, hey, I want to have course 1, course 2, course 3, and so on IDs. But the problem with this is, what happens if a student wants to take more than the number of courses that we've allotted? Well, then suddenly you have a problem where we actually can't do that at all. So then the answer may be, oh, we'll just add many, many more columns, but then you run into a problem of, well, how many is enough? And then if you overdo it, you have, for the majority of students, not even using those columns, so you're just storing wasted data for no good reason. So that's the main reason why we don't approve of this approach. Another way you may want to consider, the second way, is to have the column contain a list of values. So in this case, say student 1 is enrolled in 1110 in 1998. If we look at those courses, we would parse that list and then query in the courses table to find those courses. And as you can see, that works pretty well. And conversely, for the courses, if I want to look at all the students, I can just look at that list, and for each item in the list, query for the associated student. So at first glance, it seems like a rather okay approach, but the problem that we run into is what happens when we add new students or new courses. So say we add a third student here who's also enrolled in 1110 in 1998. As you can see, our students column in the course table is no longer reflective of the relationship. So what we have to do now is update all of the courses that this new student is enrolled in, and update by appending to that student list that we have. So as you can see, as we're adding many, many students and many courses, this the operation time goes up very, very fast, and it's not a sustainable method for storing this relationship. So then, given that we don't want to use either of these columns as lists, our third and final option that we'll talk about is the notion of a join table. So a join table serves metaphorically as a bridge between two different tables that are related by the many-to-many relationship. So as you can see here, our join table has two columns, student ID and course ID. So if we're to consider what courses student 1 is enrolled in, we would look at its ID, go to the join table, which would then tell us the course ID associated with that student, and then we could hop over to the course table to grab that information. And then the reverse is also true. If we want to see, hey, show me everyone who's enrolled in 1110, I would go to the join table, look for that particular course ID, find all of the associated student IDs, and then query on the student table to find that data. So what's nice about the join table is when we add new relationships or new students or courses and so forth, adding it is super simple. We can just add a new field. Say if student 2 wanted to enroll in CS 1998, we just add a new row to the join table with student ID 2, course ID 1998. So here's an example of how we would actually implement this in SQL. So we can set up two regular tables of student and course, ID net ID, and then ID title columns respectively. And then here's how we would want to make this join table we're talking about. So we create table join. Each join needs its own ID to keep track of itself, even though we may not use it, but then we can define the course ID and student ID column. So they're both going to be integers, the same type of the IDs in the table we'll be referencing. They both have to be not null. We don't want to have a relationship where student ID is 2 and then course ID there is null, because that wouldn't make sense in the context of our application. And then for each of these foreign keys we're defining, we have to explicitly define the foreign key reference. So foreign key course ID references the courses table ID column, and then the foreign key student ID references the student table's ID column. And then that's all we have for today. Hope you enjoyed the lecture, and we look forward to seeing you in demo.